Okay, well, a couple of different things we're going to do today. Mainly talk about IJoists, but I thought I would show you first a couple of slides that I got from this weekend. A friend of mine who lives over on Joy Road, just off of Whitmore Lake, which is not too far from here, built this little kind of a mini barn this weekend, or at least erected the timber frame part of it. So he had a little party. It was a real barn raising. Invited some friends over, and they lifted these pieces into place. And the way you do this, the way he did it, and traditionally, you build the frames flat on the ground, and they're all mortise and tenon and pegged. So you can see, I guess there's some closer pictures in a minute, you can see there are pegs that hold it together. So there's a piece from this that goes up into that, slots into it like a pocket, and then the peg holds it. And let me see if I can go through these slides. I don't know. I don't know exactly how this is going to work. Maybe not so well. Does that do it? No. Huh. Okay, sort of. I don't know. I'm trying to see where the controls are on this. If I expand it, then, see, I should be able to do that. But if I expand it, I don't see that. See, oh, there it is, okay. So, there you can see the joinery a little bit better. And these were all cut out of red oak, so locally cut trees. He had built one smaller one before, and then this was kind of, he's scaling up, and he's hoping to build an even bigger version, like maybe later this summer. But maybe, I was talking to him, I said, hey man, I could bring my class and show him this. It's not very far from campus. And so maybe, if not now, in the snow is maybe not the best time, but he's not going to do too much more work on it this winter. But then maybe in toward the end of the semester in April, when it's a little bit nicer, we might can take a little field trip and go have a look at this thing, because it really is interesting to see. Okay, let me see. Can I still go through these? Now this is probably, I think this is a video. Let's see if this plays. Okay, yeah. This is the erection of the last bent. So like I said, they build it in bents on the ground, and then they did have a little hoist there. Traditionally, you just lift this up by hand. People would push it and tilt it into place, but obviously a little bit easier. The red oak is pretty heavy wood, so that weighs a good bit. So they just lift it up on the straps, and then they position it. You can't quite see, but in the back there's another couple of piers. They had concrete foundation piers that they dropped it on. There they go. Okay. And then they brace it once you get it up into place, and they put like temporary bracing on it until they get the next set of beams connected to it. So I think that's probably close to it. They just pull it. Yeah, doing it like this, it's probably a little easier because you can position it a little on the, actually lift it. Traditionally, you position the base in and then pivot it up, so it's already at the location, and you just have to. But this, I guess this worked a little easier for him.
does it sit on the concrete, do you?
Huh?
How does it sit on the concrete, do you?
There's a little bracket that holds it. I believe that's the way I've seen it before. Let's see if we can see a. I think. How do I go? See, now I can't. Now I don't get the next. I don't know where my next thing is. I don't know why I don't get it. Huh. See, I'm trying to. There are some other slides I wanted to go through, but I get locked on this one. Maybe. Okay, let's try. See if I can go a little better here. Okay. So this one I should be able to shut. Oh, okay. There we go. Whoa, okay. So this was then from some pictures he made on Sunday. So then they did this Saturday, and by Saturday night they got the purlins up on it. And you can see here pretty much how it's pegged in place. These pieces, normally they are a little bit higher. I guess because it's so small, he dropped these a little bit lower. It's only about, well, he told me like 15 by 20 or 10 by 20 or something. It's not really very big. This is supposed to be for his 2 cows, I think. But then after he built it, Sunday he was saying, I don't know. It looks so nice. Whether I'm going to let the cows live in it, I may use it as something else, some other space. Anyway, okay. Let me see if I can still go through a couple more pictures. There you can see the pegs. There's the whole thing with the purlins on it. Pretty heavy purlins. I don't know that they needed to be that big because he's just going to put like I believe a sheet metal roof on it. Anyway, and it's up on, yeah, what you can't see too well, there should be some steel brackets that attach to right down here onto the that were then tied to the concrete, right? Like bolted, like you'd normally cast threaded rod into the concrete, and then you'd put the bracket on and screw the bracket down, and then screw the bracket into the wood. But I don't know. I can't quite see whether that's what they did or not. It looks like there's a steel I don't know. I'll have to see. I did not. I wasn't able to visit the site Saturday afternoon. My son went, and he took these pictures for me. So I haven't actually gotten to get out there and look. But okay. Anyway, thought that would be kind of fun to look at there. Let me see if I can shut that off. And then the next thing that we can talk about, I want to show you the wood of the day. And since that was all done with red oak, I thought, oh, how appropriate. We'll take red oak. Here's a beautiful piece of red oak, and you can compare it to the Douglas fir that's also kind of a reddish color. The color is a little bit similar. If anything, the Doug fir may be more red. But the red oak, if you look at the grain, very different grain, very typical, more grain that you'd expect from a hardwood, as opposed to this, which looks very much like the wide, broad grain of a softwood. The other thing that oak has that really distinguishes it, and I'm not sure what these things are called, the pores. It has these darker pores. I think they're called like did it say in here? Tulisons or something. So it has some weird name. But oak has those in particular. Tylosis. Well, no, I don't think that's quite it. Anyway, whatever. you can see it has these darker pores, which is typical of oak. Both white oak, all the oaks have those. And otherwise, the red oak, too, if you look at it closely, it kind of has holes. I mean, the grain has gaps in it a little bit. You look at that closely. You can see it's not as like solid as even the Doug fir has. There are no little holes in it, but there are if you look. And in fact, look at the end of it. If you look at the cut end of it, you'll see those pores are open in the red oak. And this is different. The other oaks are not like that. They're denser and are more suitable for anything that needs to be watertight, like a barrel. Cooperage traditionally was done with white oak. But the red oak is fairly strong. It's very heavy, dense. It's used structurally, but usually not for buildings so much. It's used, I believe, where I've heard it being used a lot is in boat docks. Even modern docks, like in big harbors like New York, where they've got these big shipping containers or big boats that are coming in. They've got to bump against something, and they don't want to bump against a piece of concrete, right? Because that would either crack the concrete or dent the boat, or it's just not. They're both. The concrete's so brittle, and it would not be a good thing to bump against. So what they often still use and have for millennia, or as long as they've been making boat docks, probably, they'll use a heavy timber, and that oak is one that is preferred for that because of its density, I think. So they'll take these big, like 15-inch oak posts and use that as a bumper. They also get used, it says here, for things like railroad ties or mine timbers, that kind of thing. What else does it say? It's heavy. It's primarily cut into lumber. Okay. Timbers, fence posts, veneer. Oh, of course, it's also used traditionally for flooring because of its hardness, its density. It makes very good hardwood floor. It's very often oak and often red oak. Okay, remanufactured into furniture, millwork, box pallet crates, caskets. I thought you had pine box caskets. What's this? Oak casket? Okay, maybe. Railway cars. So things that take an impact load. Oak might be the material that is used for that. Okay, now the other little thing I was going to mention today. Somebody came to me. Was it you? That was asking me, or no, it was you back there. What's your name? Metzok, okay. At any rate, was asking me about the reports we do in here at the end of the semester. So I thought, well, okay, I can go ahead and give you the information about that. This is something we do kind of as a special project all the way at the very end of the semester, the last few days. And the idea is to let you explore some topic in wood that you think that we didn't cover, maybe that you think would be of interest. And this can be, it's usually, you do it as a group, usually of 2 or 3. You can do it by yourself if you are really a loner, but it's a little bit easier if you do it with a couple other people. But the idea is to explore some topic, and these can be in kind of 3 different categories. One would be a case study, which is we typically do in architecture. You pick a particular building or a particular project, and you do a little bit of reading about that, and then make a presentation. And these are like 15-minute, 10-15-minute presentation to the class on that project. So we get to see, maybe a specific piece of wood architecture or how wood is used in some particular project. So that would be the case studies. You could also do a potentially physical testing if you want to do this, and some people have done this in the past. It's kind of fun. Build something and then test it. We do have moderate testing equipment downstairs. We've got a what is it? It's not Phineas Olson. A big multi tension compression loading machine, and so people have done they've actually gotten some of these and gotten a 6 or 8 foot length of it and tested it to failure and see how they actually fail. Or you could, I think last year somebody made a little truss and tested a truss. People have made box beams. We'll talk about box beams later, or a flitched beam, some particular wood element, and then try to evaluate the strength of it, test it and see how it fails exactly. And then you can show a little video to the class or whatever of the testing. And then the last option, the third option, is to do some sort of a computer analysis. So we'll take a week later on and look at STAD Pro, but of course you may be familiar with something ANSYS or whatever other finite element analysis. STAD is kind of nice because it has specifically it connects to the wood code, so you can have it do a check based on the NDS, where my NDS is. So that's kind of nice. So you could take a wood frame like that barn and draw it up and put a wind load on it and see, how strong it would be in a 100 and something mile an hour wind, and then show that, show the results of the analysis to the class. So those are basically the options. Here, you can pass these around. That would be the description of it, and it gives you a couple of examples there too. And that is all the way then, like I said, at the end of the semester. I was going to mention too, somehow we got ahead of ourselves. Let me see if I can bring up our is this out this way? Okay, there we go. A little bit here. You can look. There is eventually for that project, we'll have a sign-up sheet. I don't think I've connected the link to it yet. I'll do that this afternoon maybe, so that you should be able to click on this. This will probably go to last year's, I bet. Oh, look at that. Okay. Huh. Maybe I did update it. 2022. Totally forgot. Okay. So you can go to this page, I guess, and start to choose your group, choose a topic, however you want to do that. Okay, let's see. And then the other thing I was going to point out, I went through and revised our schedule a little bit because, like I said, I think we got a couple of days ahead. We covered the wood beams in more quickly than I thought we would. So anyway, I don't know if you pay any attention to the schedule, then this is slightly revised from what it was earlier, and we are here today. We're doing IJoists actually. Okay, so let me close that. Okay, I think that brings us up all my little announcements. Any any questions? Okay. Well, then today I thought we'd go ahead and talk about engineered wood products, specifically IJoists. There are sections in the NDS that cover engineered products. Let's see what we've got here. 5 is glulam, and then we get into composite lumber, which we'll talk about Friday. That's in 8. Somewhere I thought we had structural panels, okay. Cross-laminated timber. Oop. How am I missing it? Maybe it says it in here somewhere. So hard to keep the mouse on the... Okay, let's see if this works. Well, there is a chapter on IJoists in the NDS. Maybe it's 4. Trusses, sawn lumber. What the heck? Look in the table of contents. Composite. Oh, here we go. Chapter 7. How did I miss that? Chapter 7 is prefabricated IJoists. But most of what they'll say in that chapter, it's very short, something like three pages. It refers you to manufacturers' literature. So, yeah, chapter 7 is literally 1, 2, 3 pages. Not too much there. Okay, what these are, we can pass around these samples of them, and you can, I think we did maybe earlier, you can look particularly at the tops of these. Some of them, this one looks like it's SPL, this one is LVL, and this one is a solid piece of wood. So it's up to the manufacturer how you can see 3 very different pieces. The web is almost always OSB, but the web could be plywood as well. So they've got a good bit of latitude in how they manufacture these, and then they produce their own specifications in terms of strength. So you have to get all that from the actual manufacturer. But they're all fundamentally the same in that they have a flange right up here, this part that's got a cutout in it. This web then is tapered and is pressed up into that groove and glued. So then it's glued together, and you end up with something like this versus the solid lumber like this. So you can see it's quite a bit lighter. You also have greater control over the depth of it. Well, you can make them much deeper. Some of them are made like 30-something inches deep, quite deep, which gives them a long span. Really, the only thing that limits the span is the transport of them, right? So they could be up to 60-foot lengths, although they're usually not that long. They're usually used in residential construction, so they're more like 40-foot length max or something in that range. But they can be manufactured to be even longer. So I suppose the deeper ones probably are. 46% wood, less wood. Okay, so they're lighter for sure. Right. The only real drawback, and we talked about these before, with these is that they aren't really waterproof. So you can't use them in any exterior applications. You can't use them for a deck or something where they'd get wet, and that's mainly because the OSB will come apart. It's not going to be able to stand up to water. So I don't know, maybe if you made them with marine grade plywood, maybe you could get something that would be better outdoors, but I don't think anybody does that. There's no real application there. There is quite a bit of literature, and if you look on, of course you can look online and just find the APA has a big site. APA used to be the American Plywood Association, and then they kind of expanded their scope to include not just plywood, but basically all manufactured wood products. So they kept the name APA, but APA actually stands for the Engineered Wood Association. So it's kind of a funny thing. The anachronism is APA, but their title is the Engineered Wood Association. But they produce quite a lot of literature, and a lot of it I've put up. If you go to the Canvas site, our Canvas site, and there's a section just called Files, I think. It's just called Files. And if you look in that Files section, I've dumped a ton of literature. I mean, you can download that. I try to keep it updated. But this would be included in it. E30 is one of the main pieces of literature. I probably even have that on here. Is this E30? Yeah, this is an older one. But it includes, this engineered wood includes the IJoists, but also any of the, I think this is a pretty broad document. Includes all the, right, like it shows here, glulam, OSB, this is probably LVL, the different manufactured products. And then they also have specific literature that's on IJoists. Now this is APA that is, they're not a manufacturer, right? They're just the agency, or what would you call them? And they do have some, in this literature, they do have some charts that give spans and whatnot, but they're not generally used for that. Yeah, here they have some span. This is that, I think, 400? No, so all right, it's a different one, but this is also APA's. But the main source for when you go to design it would be directly from a manufacturer. So you'd go to like Weyerhaeuser is a big supplier, and you'd get their literature. I don't know if I have any of theirs. Maybe not with me, but in the files on Canvas, there's a bunch of their literature, and we'll look at some of their tables a little bit later. Now I've got, and I might be able to at least show you the video. I can't get the video to work in the PowerPoint for some reason. Okay. 2 flanges. Let's see.
And a web that are joined together to form the distinctive I shape that gives IJoists their name. The flanges are either solid sawn lumber or structural composite lumber, usually laminated veneer lumber or LVL. The webs are usually manufactured from oriented strand board, but can also be made with plywood. The IJoist manufacturing process begins with the production of the flange and web components. To make flanges, Sections of laminated veneer lumber or sawn lumber are finger jointed at the ends with adhesive applied in the finger joint to create long lengths. In this manufacturing sequence, solid sawn lumber is being used in the flange assembly. In another area of the plant, oriented strand board is delivered to the line, where it is cut into 4-foot-long web sections. The depth of the webs varies depending on the depth of the finished I-joists, which range from 9.5 inches to 32 inches. After web sections have been cut to the required size, a bevel profile is cut into the top and bottom edges where the web sections will be joined with the flanges. Plywood can also be used in web fabrication.
So there's the beveled edge.
The web sections and flanges come together in the assembler. As the flanges move into the assembler, grooves are cut in the top and bottom flanges and adhesive is applied in the grooves. In a fast automated process, the profiled edges of the web sections are inserted into the flange grooves and a permanent bond is formed. As the I-joists come out of the assembler, they are cut to long lengths, with the length depending on the manufacturer. These lengths may range from 24 to 56 feet or more. The assembled I-joists are checked for glue bond integrity and other visual characteristics, trimmed to their final length if required, and then moved out into the yard for packaging and shipping. Manufacturers that adhere to the APA performance standard for I-joists, PRI 400, monitor quality with a strict in-plant testing program that is audited by APA. This shear test is one of the daily quality assurance tests that is performed. Tests like this, combined with a carefully controlled manufacturing process, ensure consistent quality and performance in the finished product.
Yeah, it looks like that shears right at the web shears at the edge, I think is what that did. Okay, let's see. Okay, now I don't know whether I want to use this pen or not. It's to lock the whole thing up again. Okay, let's just say there's the Weyerhaeuser literature. Okay, there's also in the NDS, like I said, this chapter 7, and if you look at chapter 7, basically what it tells you is to refer to the manufacturer's literature, like this 7 reference design values. It says all reference design values for prefabricated wood I-joists shall be obtained from prefabricated wood I-joist manufacturer's literature. So they, in the NDS, they simply point you to that. They do have a few factors that you could apply. Mainly just the low duration factor would be the one that would potentially get applied. Moisture factor, like I say, generally they're not allowed to be used in moist conditions, so they don't usually use a moisture factor. Temperature factor, I guess, would be one that could be applied, but even that, it's saying to refer to what does it say? Reference design values. Oh, yeah, the same as for wood. Dimension lumber is 233. Okay. All right, let's not try to play that. Okay, let's see if I can show you at least the video. Whoa, okay.
Hi, I'm Randy Melvin. Today I'll be talking about the advantages of a cost-effective wood I-joist floor system that relies on thicker and stiffer floor sheathing to deliver a premium floor assembly compared to typical lumber framing. I-joists are premium engineered wood floor system components that are capable of spanning greater distances while reducing labor costs and speeding floor construction. they have some other significant advantages as well. I-joists are manufactured to demanding standards. Their high strength and long lengths increase design flexibility and can reduce the need for supporting beams and columns, creating the open, unobstructed spaces today's home buyers are looking for. I-joists' consistent dimensions and low moisture content mean little or no shrinkage that may cause squeaky floors and nail pops, which can result in callbacks. The specific floor system that we see in this home uses deeper, stiffer, and stronger I-joists and thicker floor sheathing. The floor sheathing is 7/8 performance category wood structural panels. It is glued and nailed to deeper I-joists that are spaced at 24 inches on center. 7/8 floor sheathing is typically rated for 32 inches on center joist spacing, which means that it provides a very stiff floor system when I-joists are spaced at 19.2 or 24 inches on center. Most builders appreciate the benefits of a wood I-joist floor system, but roughly half the builders in the U.S. still have not made the switch to I-joist. This particular floor system is one that builders who haven't made the switch really should consider. It uses 14-inch deep I-joists spaced 24-inch on center. There can be several types or series of 14-inch joists that can be used in such a system. Your lumberyard or engineered wood supplier can help you determine which joist to use, as well as provide you with a complete floor system layout. The 7/8 flooring makes an incredibly stiff floor feel. The wide spacing of the joist makes it easier to keep the ductwork and plumbing within the interior of the home, which is more energy efficient and can help reduce the cost of meeting today's energy code. Even though the thicker sheathing and deeper I-joists cost a bit more, those costs are offset by the material savings alone. So you get a premium floor system installed for about the same cost. Depending on the performance expectations of the floor and the loads that must be accounted for, the number of joists can be decreased by more than 1/3 compared to the typical lumber floor system. This drives a lot of savings, including 1/3 fewer joists to install by the framing crew, 1/3 fewer fasteners and hangers used to install the joist, 1/3 less floor construction adhesive, 1/3 less floor sheathing fasteners, and 1/3 fewer holes to drill for running ductwork, electrical, and plumbing. Additional savings are typically realized, as is the case with this project. The deeper I-joists permit the designer to use just one joist in several places where double joists have previously been called for. The floor system also allows the home to get under roof faster, which means the interior is protected from the elements sooner. And it allows quicker returns on the builder's capital by reducing time under construction. For more information on engineered floor systems, visit the APA website at www.apawood.org or call our help desk at 253-620-7400.
Okay, so that's APA's. Whoops. Actually, the argument I've heard generally, the only argument really against these two things. One is, of course, they're not waterproof, so you have to be careful of naturally never exterior. But even, I mean, I'd be very cautious in using it like under a kitchen or under a bathroom, because there's just so great a risk that you're going to have a leak that's going to, get on it, and then if that destroys the joist, then you've got a real problem. That's much more hard. That's more difficult to repair than if it just, got a dimension lumber wet. Really wouldn't make much difference in the short term. You'd probably notice it. So that would be one drawback. The other is it is more expensive. And he makes the argument, well, the expense is balanced out because you're using them at, wider spacing, 24 inches on spacing. So then it's the layup of it is quicker. Okay, I guess maybe a little bit quicker. The fewer fasteners. Well, the nails aren't really that expensive, are they? But okay, maybe a consideration. Anyway. So those would be considerations, I guess. The other thing I could maybe, let's see if we can, I had one other video that talked specifically about the the gluing. And this is, you'll notice that all of that construction was glued and nailed. And the glue makes a much better bond than you get more continuous, and it's better bracing, and there are a lot of and even with dimension lumber, gluing is commonly used. And I think, let's see if we can.
Another important step is to use a glue-nailed floor system. Be sure to clean moisture and other debris off the joist before applying glue.
Okay.
Extensive APA testing shows that glue firmly secures panels to the joists and gives floors more stiffness than non-glued floors. Glued floors go down quickly, using regular construction materials and techniques. Spread only enough glue to lay 1 or 2 panels at a time, so you can finish nailing or fastening before the glue sets up. Remember, warm weather will cause the glue to set faster. In cold weather, keep the adhesive cartridge warm so the glue will flow evenly. Apply a continuous bead of glue to the band joist and all framing members. On wide framing areas, apply 2 or more lines of glue. And be sure to bond all tongue and groove joints together by applying glue in the panel groove. On joist where panel ends come together, apply 2 lines of glue to assure each panel end is secure.
So the gluing is a good technique. I used to have a friend that always specified glued and screwed, but it's much more commonly nailed than screwed. Although screws give maybe a better connection, nails are certainly fine. The one thing that you might, if you're in a position of ever inspecting some construction like this, that you have to watch for is that the nails actually hit the joists. If you watch those guys when they nail, they've got, this isn't done with a hammer and a nail anymore. There's a gun, right? And it's just bang, 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 bang. And you don't really, when you're doing that, you don't have a feel for the, I mean, you just pull the trigger or whatever it is. You don't have a feel for whether the nail went into a board or missed it. So what'll happen is you'll have the joist, right, and the decking over it, and they'll nail it here and miss the board. So if you look underneath, you'll suddenly see a whole row of nails that miss the joist. And of course, that is part of the strength. You can't leave out the nails. So if somebody's missed all those nails that needs to be gone, they need to go back and put the nails in the right spot. And this is particularly critical for roofing. There are a lot of failures in high winds because you get a high suction load, right, on the roof from the wind, and that'll rip the panels off. And a lot of times when that fails, it's because they didn't nail it. They didn't get it. They missed it. You know, they did nail it, but they missed the joist or missed the rafter. So you have to be careful that gets connected. Okay, so this is APA's literature. This isn't going. Hopefully, they're gone. Okay, so this is some of APA's literature, the Z725, and they go through and they give several examples of how it's not so much tables of strength, but how you apply it, how you use it. And it is a system, you know, like in that video they were showing the layup of it, and they were using the 7/8 inch OSB on top of it. And there's also, they didn't mention, but there's also a rim board, a rim that goes around the edge that provides end bracing. And you have to use the correct rim board with it. And they deliberately make these things different sizes from the dimension lumber. Like, I'm not sure what this is. I think maybe it's 9.5 instead of 9.25, but it's not. If you put dimension lumber next to it, it's a different size. And they do that deliberately so you don't mix it, right? They don't want you to use this and then dimension lumber and then, you're not supposed to mix it. You're also not supposed to mix it like for the rim board. You're not supposed to use dimension lumber. You're supposed to use either LVL or some piece that's manufactured specifically as rim board for this application. So that's the, okay, let's see if I'm going to screw this up. Okay, no, look. Okay, we're back to, I guess I'll just have to leave those videos out. All right, anyway, so that's, and there's some other illustrations. I don't know if I have one in here that they show. Let's see. This is different methods for bracing. This, actually, here they are using, I believe, dimension lumber is sometimes used for bracing because it deliberately leaves a gap there because of the different expansion rates. But this would be for to strengthen it over a support. So where you've got this coming in, particularly if there's a mid-span support, and that would put a lot of shear on the web, and there'd be a danger of the web failing in shear because of the high shear at the support. So to strengthen the web, they'll do this. You'll nail in bracing. And there's specifications for that, how long that bracing has to be and where it's placed, that they may be in this piece of literature, but they're also in the manufacturer's literature. You could see exactly tables of exactly how big that should be. The other issue that you deal with are holes, and a lot of times, let me see, some of these may, I don't know if any of these show, these are such short pieces, they don't show it. A lot of times, oh yeah, ah, look at that, this one does have one. They'll cut a hole, if you look at this, they punched a hole in it already, and all you have to do at the site is push that out. Okay, maybe if you have pliers or a hammer or something, you can push that out. But you can see they pre-cut that pre-cut that hole, and they'll do that with bigger holes as well. And they'll tend to, I think they usually put them in the right locations, but maybe not so carefully. There are limits. You don't want these holes to occur where where the web would be subjected to a high shear. So the web is always going to be weaker in shear, right? The top and bottom flange take the tension and compression from the bending moment, but the web is going to carry the shear. So wherever you've got a high shear, you don't want to damage your web, and you have to be careful. At the ends, then there are limits to how like that minimum distance as to how close you can get to the edge here, the edge support, and that just has to do with the shear. The other thing that they generally try to avoid are sharp corners. In the ones they manufacture with the cutouts in them, they give you a nice circle. Usually, if you can't cut a circle, you at least come in and you cut circles at the corners here, and then you saw it around so that at the corners you have a rounded edge, because that would be the sharp corner is a concentrated stress, and there'd be a danger that it would crack. So rather than risk that with a big hole, they usually try not to have them rectangular. And most of the stuff you're running through it, ductwork, is usually circular. I don't know. I guess we have square ducts too, though. You have to be careful. Do not do that. Never cut through the top or bottom flange. So that would be a big no-no right there. That destroys it, of course. So any of these, where they're cutting through the flange here in some way, or this is the situation without those circles. So they should have a circle, cut first there to give it a little better stress. Okay, this is probably Weyerhaeuser's literature. So this is typical of the manufacturer literature, and you can see they get very specific then in the table for exactly the certain depth, and then the certain grade. There are 3 different grades, and then the distance, the size of the hole, and then this is giving the end distance, this minimum distance here, this distance, I guess. And so you read that distance right out of that table, either for round holes or for square holes, depending. So based on your size and the size of the hole, you can see exactly in this table exactly how far it has to be spaced. Then Weyerhaeuser also has, this is a little bit more description just of the whole system. Here's with a cantilever and bracing the cantilever. That would be against shear in the web. Here's an attaching piece here, so they brace that. The rim board, I guess, is shown on here. Here we go, the rim board. All right, so, and then this is some of Weyerhaeuser's. This is a properties table, right? They give properties tables, which is kind of like the NDS properties, the different stress limits, although they'll do it in terms of force, so it'll be with moment or shear, right? In terms of force, and then they'll also give apparently EI, all right, and maximum end reaction allowed. Okay, so you can look in this table, and this would give you. This isn't a span table. This is the actual moment, and so if you had one that was a little bit unusual condition, maybe it has some point loads on it, maybe it has, it's not just a regular uniform load, because all the span tables are just set up for uniform loads. So if you have anything unusual, you calculate the moment in the shear, and then you go to a table like this, and you can also see this does the deflection calculation. It includes shear, right? This is your regular bending moment, and then you have the web shear deflection. Normally, any beam has deflection due to shear, but it's usually very small, and you just neglect it. But with these, because the webs are a little weaker and particularly susceptible to that shear deflection, they'll include the shear deflection in the deflection calculation. So that's what that second term is there, including the shear deflection. So those are simply the equations you'd use to calculate deflection then. Okay, so what else we got? And then this is a typical span table, right? It's set up for a deflection limit, the live load deflection of 360, and you've got a choice of either, these are residential loads, right? 40 with a 10 PSF dead load or a 20 PSF dead load. So depending on your dead load, that pretty much, I guess, covers what you're likely to hit in a residential construction. And then you can see, you just read it out of the table. For any particular size, particular grade, and then the on-center spacing of them. This 19.2, I think that's that must be 5. If you take an 8-foot span, 8-foot sheet, and divide it into five sections, that's where that 19.2 is coming from. Right. So, okay, yeah. And then you just pick it out of the, you pick the your span out of the table. So your load, your type, and your spacing, and then you'd have a specific span that you could span 19 foot 4 inches. So as long as you don't exceed that, then that's all the design that you'd need to do. This one is for a stiffer floor. This is L over 480, and here you've got, I mean, they show both. They show, I think this is the limit. This is being limited by the total load. This is the total load, I guess, and this would be the total load limit by the deflection. So here the total load by strength would be 152, but if you're limiting it to L over 480, then it's a little bit less. It's 140, and the ones with the asterisk, they would meet that 190, and I mean, in other words, at 190, it would meet the L over 480 criteria. So again, with this, you are able to, well, this is a load table, right? It's not, well, I don't know, I guess you could call it span. These are all the different spans. It gives a span, and then you pick the load for that span and the member. So you're able to read the load capacity off of it. It's a load capacity table, really. Okay, so let's see. We can even do an example here, I believe. This is supposed to be an example of joist selection, right? So first you got to get your load, then you decide what your limiting deflection is going to be, either the live load of L over 360 or the 480 limit. Pick a spacing, and then you just go to the table and pick your span. Or you can calculate and do it with the, you can calculate the shearing moment and do it that way. Okay, so let's try it. There's a little example. We'll do one of these. I think this is based on one of these guys here. Has a span of 16 feet. They're 24 inches on center. Have a dead load of 10 PSF and a live load of 40 PSF. Okay, and we'll say, I think I'm using the table. We'll see. It depends on the tables as to whether you're at the L over 360 or 480. So here's this is then the total load. If I want to use those total load tables, right, this is 24 inches on center, so the dead load would be 20 PLF. The live load would be 80, so I got 100 total. I could go to, this is the table that gave me the loads. So if I want to do it based on that, here's my 16-foot span, right? And if I want to limit it to L over 480, then the live load would be at 80. And actually, my live load was 80, right? Was what I had for the live load. So that would pass this, and the total load could be as high as 119. My total load was only 100, so it would pass that one too. So that would work. That would be that, these are different grades, right? And this would be the depth, a 11 7/8, 230. They probably have that stamped on them, don't they? I thought some of them did. Well, maybe I'm wrong. Okay. They usually have that grade stamped on them. that you can see what they are. Okay, so that's pretty straightforward. Then the other way you could do it, if you didn't want to meet the 480, you could say a live load deflection of L over 360. This one looks like it would pass. This is my 40 and my 10, right? That's what I was using, PSF. So this looks like I'd get by. This is 16-foot span. I'd get by with a 9.5. So if I don't need the extra stiffness of the L over 480, I could drop down. This would mean my floor would be slightly more bouncy, right? This is the traditional in the IBC limits on deflection. I think this is what they give is L over 360. That L over 480 is more recently they've been touting that as sturdy floors. They're extra, stiff floors, and they really are only achievable. I think they really only meet that with these deeper I sections. Okay, so this is then the same problem, right? But this is with, if you want to calculate, doing it calculating the shear moment. Remember, there were other tables that gave the properties. So if I go through and calculate the shear and moment, this is based on a total, right? This was the total. This was the 80 plus 20 PLF. So that comes out with a total moment of 3,200, and the shear is at 800. Okay, so then you can go into their table here, and it looks like this same one does pass. Now this, I'm not, well, maybe I do calculate I have to calculate the deflection separately. So here is the, what did I need? 32, and I've got 33, so that passes, and this is way high. I think I only needed 800, so that one would pass, right? The next one down would fail, though, because this one would be too weak, but that one would pass. I could go to a deeper one. I could have picked one like this. Oh no, that one would fail, but this one would pass. Right? I had 32. I think wasn't that what my moment was? Yeah. Okay, 3,200. So that one would fail, but this one would pass if I wanted to do it with a deeper section. And it's a slightly lower grade, 210. I'm not sure what that comes from. Okay, so then we can also calculate the deflection separately. I think I did that here. So here's the deflection calculation. This is the EI value that was out in that other table, I believe. Let me check. 200. Where is it? Okay, take it back. I guess it's in yet another. I thought it was in this properties table, but they're in the same literature. There's another something. Oh, here it is. No, I'm sorry. I'm not paying attention. There it is. 206 times 10 to the 6th. Okay. So that's where that came from. 206 times 10 to the 6th. And right, and then we multiply, and I'm using the depth. There's the D for that 9.5 member. So the shear deflection, it's small, but it's not totally negligible, right? That's the shear deflection, and this is the bending deflection. So it totals out to be a little over ½ an inch, and the limit on L over 360 is actually, so it looks like it would actually fail that L over 360. So I don't know, that other table indicated that it actually passed, right? The L over 360. I mean, it's pretty close. Maybe they figure that's close enough, or I don't know, but in their other table they showed that as passed. It definitely fails the L over 480. Anyway, so for what it's worth, that's the actual deflection calculation then. Okay, I think we've gone through enough of that. You can have a look at the literature that's up there in the Canvas site, and it should, like I say, I hope it's up to date. But you probably should just make a note. You might want to go to the Weyerhaeuser site and just look at the information they have, or APA. There's another one. I guess Truss Joyce is Weyerhaeuser, isn't it? There's a lot of literature that's Truss Joyce is spelled with one S, TRUS/Joist, and I think that is Weyerhaeuser that produces that. That's maybe one of their trade names. Anyway, you can have a look, and that's, for as far as designing, it's mainly done just with the tables. You get the manufacturer's literature and pull the pieces out of the table. Okay, very good. Next time we'll talk about the other manufactured products. Have a good week. Stay warm, out of the snow. You can avoid it.